Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means. This video is going to tackle topic 7.6, confidence intervals for the difference of two means. So what are we trying to find here? Now let's recall what a confidence interval is. This is actually the fourth time that we've seen a confidence interval. A confidence interval is trying to find a population mean. We actually started off in Unit 6 trying to find the true population value or proportion from a population. Then we looked at the difference between two population proportions. And then most recently in this unit, we looked at trying to find the true mean of a population. And now what we're going to do is we're going to look at trying to find the true difference between two population means. So we're going to examine two entirely different populations and examine the mean blank of each population. So maybe we're going to look at the mean heights of two different populations and compare them. Maybe we're going to look at the mean weights of two different populations and compare them. Maybe we're going to look at the mean amount of something from one population versus the mean amount of something from a different population. Or maybe we're going to look at the mean size of one population versus the mean size of another population. So the idea is that we're looking at two different populations and we're going to compare the means from each of those populations. So what are we looking to find here is the true difference between those two population means. So we're trying to find the true difference between those population means. Now I've discussed this way back when we talked about proportions, but the order you subtract does matter. You know, generically we're going to use ones and twos, but you have to understand that when you subtract two numbers, first and foremost, you only get a single number. If that number's positive, well, that's going to tell you the mean from population 1 is going to be bigger. If the mean is negative, or excuse me, if the difference is negative, then that tells you that the mean from population 2 is going to be bigger. Because if you take a smaller number minus a bigger number, you're going to get a negative number. Or you could even end up with a difference of 0, and that would tell you that these two values, the mean from population 1 and the mean from population 2, are exactly the same. So those are kind of the three different outcomes that can happen, but it really does matter the order that you subtract them. So let's take a quick visit backwards in time to Unit 5 when we first started talking about sampling distributions. Now recall a sampling distribution is used to find the difference between two population means, right? That's kind of what we're doing, right? But if you recall, when we looked at that back in Unit 5, we said, all right, we know that the mean and standard deviation from one population, and we know the mean and standard deviation from a second population. Okay, great. So if we know those values, then that means if we could build a sampling distribution, and a sampling distribution shows us all possible differences between a sample from one population and a sample from the other population. So that's what we're looking at right here. We're saying, all right, what is the mean of all possible differences between samples? If I take a sample from population 1, if I take a sample from population 2, and I look at the difference between them, who knows what I'm going to get? But if I do that repeatedly, what's the mean of all those differences going to be? And that is, of course, right there, the true difference, right? That makes complete sense. Why wouldn't we expect the true difference to be right smack dab in the middle of our sampling distribution? But then we also understand that those many differences between any two samples is also going to deviate. So that's where we have the standard deviation of the sampling distribution for the difference between two samples. Well, take a look at this formula. We learned it all the way back in Unit 5. But you take the standard deviation from population 1 squared divided by the sample size plus the standard deviation from population 2 squared and divided by the sample size, and a giant squared around all of that. All right, and that allows us to build this sampling distribution, which as long as we meet our conditions is going to be normal. So right smack dab in the middle is the true difference between the two different population means. But we know that, a sampling distribution is filled with many different sample differences, and some sample differences could be a little higher, some sample differences could be a little bit lower, and that's where the standard deviation comes in. So the problem now arises is this. We have to work backwards because we don't know the true mean of population 1. We don't know the true mean of population 2, nor do we know the standard deviations of the two populations, which means that we cannot find the difference because we don't know the true difference. We don't know the true means. We cannot calculate the standard deviation because we don't know the standard deviations of each population. But it's important to understand, yes, we have no idea what the true population mean of each population is, and we have no idea what the true difference between these two populations means is going to be. But that sampling distribution does exist. It is out there. I can visualize it, meaning that somewhere out there is the true difference, and somewhere out there is the true standard deviations that would allow me to build that sampling distribution. Unfortunately, I just can't do it, but it doesn't mean I can't visualize it. So the idea here is all that I can do. You know, if you don't know something, the only thing you can do is take a sample. I could take a sample from population 1 and get a sample from that, or get a mean from that sample from population 1. That would be this guy right here. I can get a sample from population 2, and I can get a mean from that sample from population 2. That'd be this guy right here, and I could subtract them, right? That would be the difference between my sample means. Now, again, I can't build this sampling distribution, but it doesn't mean it doesn't exist. So somewhere out there, this does exist, and right smack dab in the middle is the true difference between the population means. Mu minus mu. Sorry, it's kind of small there. But the idea is that my difference, the difference I found, it's in here somewhere. And I'm going to bet with a lot of my money that it's somewhere in the center. It would be really, really unusual if my difference was extremely, extremely high or extremely, extremely low. I'm going to go ahead and bet that my difference is somewhere really close to the true difference. So the idea is very simple. If I take my difference and I wrap an interval around it, I'm probably going to catch the true difference somewhere in my interval. So again, we've walked through this process. Again, this is the 4th time we've walked through this process. If my difference was on the high end, when I build that interval, voila, I caught the true difference. Or even if my difference is on the low end, when I build that interval, voila, I catch the true difference. So the idea is that we don't know that sampling distribution. I can't see it. I can't create it. But I could think about it. And I could think about the only thing I do have is a difference between my two samples. And as long as I understand that most samples, and again, if you're going to do 95% confidence, 95% of samples are going to be so close to the truth in the middle that when you build that interval, it will create or will capture the truth in the center. So what we have to do moving forward is think about how could we build this interval. Now, the only things I know are the means and the standard deviations of my samples. So we are going to have to use the T model here. The idea is that I can't use standard deviation because remember, I don't know the population standard deviations. The only thing I do know is the standard deviation from my first sample and the standard deviation from my second sample. So I'm going to have to use standard error here, which is, again, it's the same formula. All I'm doing is replacing the population standard deviations with my sample standard deviations. And all this means is that that sampling distribution I'm trying to envision, it's going to follow the T model. We've talked about this. We've dealt with this. This really should be no big deal. Okay? So the only thing we have to do now is really just walk through the steps. And you know what? This is kind of getting secondhand here because we've done this so many times by now. So how do we find the interval? First, we have to name it. This is a a 2 sample T interval for the difference between two population means. Make sure you use context here. Make sure that your name is discussing what the two different populations are that you're comparing. Next, we have to check the conditions because even though we can't build that sampling distribution, we're still envisioning that it does exist. So we do have to check the conditions for that sampling distribution to be built, and we have to make sure the conditions are checked for each sample. Finally, we have to build the interval. This is actually the easiest part. We're going to take the difference that we observed between our two sample means, and we're going to add and we're going to subtract a margin of error. We'll give you that formula in the next slide here in a moment. And then finally, we have to interpret our interval and make sure that we can explain what our interval is telling us in context. So here is the official formula for a 2-sample t-interval for the difference between two population means. It's actually quite easy. I mean, I know I've been talking for a little bit of time now, but when you sit down and actually look at how to build this interval, it's unbelievably simple. So first, we're going to start with the difference we found between our 2 sample means. Now, we're pretty confident that that difference is really, really close to the true difference. Hence, if we add and subtract, that's where the plus minus comes in, the margin of error, we will capture the true difference somewhere in our interval. All right, so how do we find that margin of error? Well, first, we need to go up and down a t star. That's a critical value. Again, can't use z here. It's because it's not a normal model. Because we're using our standard deviations from our sample, we got to use a t model. And we'll talk a little bit more about that in a moment as well. Just remember, there's actually many, many t models, not just one, all based on your degrees of freedom. And then the only other thing we need is that standard error formula I already actually mentioned. And that standard error formula is simply the standard deviation of my sample from population 1 squared divided by the sample size plus the standard deviation from population or sample 2 squared divided by the sample size that I took from population 2. And that's the standard error. All right, so recall when we use sample statistics in place of population parameters for the standard deviations, it's called standard error. So don't forget that back part right here is called standard error, not standard deviation. All right, now keep in mind the level of confidence here. Now remember, the level of confidence is what tells us how to find our t star. So if you remember to do this, I actually already showed you, so let me bring my calculator to the screen here. We're going to go to second vars and we're going to get a invert t, and this is how we're going to find our t star. So when you go to invert t, it's going to ask you for the area at the bottom, and this is something we've been doing for quite a while now. So if we want to be 95% confident, that puts 0.025 or 2.5% at the bottom. And then we also have to type in our degrees of freedom. So let's talk a little bit about degrees of freedom real quick, because if you remember earlier, the degrees of freedom was simply sample size minus 1. But now I have 2 samples. So let's talk a little bit about this. How many degrees of freedom do we have when working with 2 samples? To be honest, it's crazy, but the official formula is very, very complicated. It's actually really weird to me because when you're talking about 1 sample, the degrees of freedom is like, it's mind-boggling easy. It's just your sample size minus 1. But the moment you're working with 2 samples, the formula for degrees of freedom is like unbelievably complicated. And excuse me, no one's really ever going to want to use that formula. So listen, here's the good news. We're not going to use that formula. Okay, so what we're going to do is we're going to simplify it, and simplifying it is I'll be honest, it's technically wrong, but it's a lot easier and it's okay for this class. Now, if you're going to take advanced stats in college, yeah, you might want to end up using the official formula, but I'll be honest with you, in this class, and I'm not just doing this for me, this is the officially from AP, in this class, it's okay to use a couple other easier methods to find the degrees of freedom. So we're going to use a very simple method. It's so easy. All you're going to do is you're going to find the degrees of freedom from your first sample, find the degrees of freedom from your second sample, and then just use the smaller of the 2. That's it. It's that simple. So we're not going to use a very complicated formula. You're just going to find the degrees of freedom from each sample and use the smaller of the 2. Okay, it's that easy. So let's just say we have a sample size of 39, and then we have a sample size of 50. Okay, so that's 38 degrees of freedom here, 49 degrees of freedom here. So you would use the smaller of the degrees of freedom. So when you go to your calculator, the degrees of freedom you'd use would be the 38. And that is how you would get your T star. So a little bit weird. Don't overthink that, but that is simply how it is. All right, so I think we're ready now to just dive into an example. It's quite simple. I think you'll find it pretty easy. All right, do American teens read more books than Canadian teens? I don't know if anybody ever wondered that. I don't know. Do American teens read more books than Canadian teens? Well, researchers wanted to answer that question. So a sample of 54 random American teens had a sample mean of 5.3 books read per year, with a standard deviation of 1.8 books. A separate sample of 48 Canadian teens got a sample mean of 4.8 books per year, with a standard deviation of 1.3 books. So what I'm trying to find is the true difference between the average number of books read by an American teen and the average number of books read by a Canadian teen. And I want to know the answer, and I got to try to figure this out. So I want to construct a 90% confidence interval for the true difference in the mean books read per year between American and Canadian teens. So here I go, diving into the 4 steps. Step 1 is literally just naming what you're doing. This is a 2-sample T interval for the difference between the mean number of books American teens read per year and Canadian teens read per year. So please make sure, first and foremost, you have this part right here. This is super important. That's the official name. It's a 2-sample T interval for the difference. Then you got to give the context. Difference between what? Oh, the mean number of books read by American teens and Canadian teens per year. So please make sure you give that nice official name there that has all the pieces and parts. Now, another thing I like to do in step 1, but this is not part of step 1, is I like to just get all my data organized, right? Get everything organized. So I have the information for the Americans. 5.3 was the average number of books read. 1.8 was the standard deviation. 54 was the sample size. And then I have my Canadians. 4.8 was the average. For the Canadians, 1.3 is the standard deviation, and the sample size was 48. So I'm going to go ahead and take the Americans minus the Canadians, and that was 5.3 minus 4.8, and that was an average difference of 0.5. So the difference between my 2 samples was only a half a book. 0.5 books was the difference between my 2 samples. But I have to admit that that's not the true difference. That's just the difference between my 2 samples. So now I want to build that interval that goes up a little bit, down a little bit in an attempt to try to find the true difference. Now, what I want to do is I want to think about that sampling distribution because it does exist, and the right smack dab in the middle is the truth. And I don't know where I fall. I don't know where 0.5 falls. Maybe it falls on the high end. Maybe it falls on the low end. I don't know. But I'm gambling. I'm 90% confident that it's so close to the truth that when I build that interval, the truth will be contained. So because I'm referencing that sampling distribution, I got to check the conditions for it. So first, these should all sound very familiar. The data was collected from 2 random independent samples from their populations to avoid bias, so that they were random and independent. All right, since we are sampling without replacement, we need both samples to be less than 10% of their populations. So I'm going to go ahead and assume, pretty confident, that 54 American teens is less than 10% of all American teens, and that 48 Canadian teens is less than 10% of all Canadian teens. So independence is assumed. And then finally, I want to make sure that I can use a t-distribution, and both samples are at least 30. Both samples are well over 30, so it's going to be completely okay to use a t-distribution, and I'm going to go ahead and use one with 47 degrees of freedom. So let me just review that real quick. Remember, for the Americans, I had 53 degrees of freedom. For the Canadians, I had 47 degrees of freedom, and the rule that we're going to use is we're going to use the smaller of those 2 degrees of freedom, so that's the 47. All right, so now it's time to build the interval. So what I actually like to do is kind of rewrite the formula real quick and then just start substituting everything in. So the first thing is the difference between my 2 samples, which was 0.5. That was pretty easy. Actually, I already found that. Now I need my T star. Let me show you how I'm going to get that real quick. So I'm going to go to second vars. I'm going to go to invert T. And I wanted to do a 90% confidence interval. So if I'm doing a 90% confidence interval, I put 0.05 at the bottom. And then I need my 47 degrees of freedom. And this is going to get me that wonderful T star I needed, 1.6779. And then finally, I need my standard error in the back. And this is where I got to be very careful to make sure everything is correct. For the Americans, it was 1.8 squared divided by 54 was the sample size for the Americans, plus 1.3 squared divided by 48 for the Canadians. Now, to get the margin of error, I highly recommend just typing all of this into your calculator at once, 1.6779. And then I need a square root. And again, no parentheses. Your calculator is pretty smart here. You could just do 1.8 squared divided by 54 plus 1.3 squared divided by 48. And the calculator is pretty good to do all that math. And you get 0.5177 as the margin of error. So now I'm just going to take my 0.5, subtract 0.5177, add 0.5177, and I get my interval. All right, now it's time for step 4, and I have to interpret what the heck that interval tells me. All right, so very generically speaking, here's what that interval tells me. I'm 90% confident, based on the samples taken, that the interval from negative 0.0177 to positive 1.0177 contains the true difference in the mean amount of books read per year between Americans and Canadian teens. But I'm going to be honest, I hate that. I would never recommend doing that because it doesn't really truly tell us what's going on. That type of interpretation doesn't compare at all. My job was to compare American and Canadian teens and how many books they read. So let's use these same numbers from my interval, but let's do it a lot more common sense way. Now, the first thing I noticed is that one number was negative and one number was positive. Remember, I specifically subtracted the American value minus the Canadian value. So a negative would actually tell me that the Canadians read more books on average. The positive would tell me that Americans read more books on average. So a much better conclusion is this. I'm 90% confident, based on the samples taken, that the American teens read anywhere from the 1.02 more books on average per year to 0.02 less books per average or per year than Canadian teens. So again, the positive number was the 1.02. That's going to tell me that the Americans could be higher. The negative number, sorry, my negative was right there. The negative 0.02 tells me that the Canadians could be higher. So the Americans can be anywhere from 1.02 more books on average per year more to minus or less 0.02 books less per year than the Canadian teens. That's a much better answer that truly interprets what you're looking for. Okay? Now, since this interval tells me that the Canadians could read more books, Americans could read more books, and you know what? 0 is also in this interval, so there might even be no difference whatsoever between Canadians and Americans in terms of how many books they read. All right, now let's just play a quick what-if game. What if this was our interval? I just want to make sure everybody understands this. What if our interval was entirely positive? I'm just making these numbers up, 0.07 to 2.3. If this was the case, it's all positive. Well, remember, I did Americans minus Canadians, so this all positive interval would give me pretty good evidence that Americans read more books. This would tell me I'm 90% confident Americans read on average 0.07 more books per year to sorry for the double decimal there, 2.3 books more per year more than Canadian teens. So an all positive interval would tell me that the Americans are going to be more than the Canadians. If it was all negative, then that would tell me the Canadians are more than the Americans. But what actually happened was I got a negative and a positive, which tells me that, you know, that the Americans could be higher, the Canadians could be higher, or you know what? There could even be no difference. All right, so let's take a breath. Hopefully that was all, you know, fine and dandy and pretty easy. And let's look at one more example. Wildlife researchers are interested in finding the difference in tree sizes between oak trees that grow in northern states and oak trees that grow in southern states. To estimate this difference, the researchers analyzed 40 random oak trees from the north and 40 from the south, and they measured the diameters in inches of those trees at a height 2 feet above the ground. So the reason why they did 2 feet above the ground was to stay consistent, because obviously trees get skinnier the higher up you go. So we measured every tree 2 feet above the ground just to try to stay consistent when we're measuring the trees. And we measured them all in inches. It would be obviously silly to measure each different tree in different units. And it's kind of cool here. We actually did 40 from each population. You don't have to have the same sample size, but here we did. All right, now here's my data. From the 40 trees from the north, the average was 36.6 inches in diameter, standard deviation 12.8, and the average for the southern oak trees was 28.9 with a standard deviation of 15.4. So I'm going to do my north minus my south. So a positive is going to mean that the north is bigger, which is obviously what happened in my two samples. But again, a negative would mean that the south was bigger. All right, so it wants me to create a 95% confidence interval for the difference between the mean diameters of oak trees in the north and oak trees in the south. So here we go. So this is a 2-sample T interval. There's that name, 2 sample t-interval for the difference. Now you got to give that context. The difference between the mean diameter of oak trees in northern states and southern states. So that's what I'm looking for. I'm looking for the true difference between the mean from the north and the mean from the south. That's what I'm trying to find, and I need a 2 sample t-interval to try to find it. All right, so let's check those conditions. The data was collected from 2 random independent samples from their populations, one from the north, one from the south, to avoid bias. Since we're sampling without replacement, we do need each sample to be under 10% of the population. To be honest, when you're doing this on a test, you don't have to say this, right? I'm just explaining to you in this video why we need that, okay? You just have to say, hey, 40 oak trees is less than 10% of all oak trees in the northern states, and 40 oak trees from the south is less than 10% of all oak trees in the south. Pretty sure there's lots of oak trees out there, so that independence is assumed. And then finally, both samples are 30 or more, so that we can use a t-distribution with 39 degrees of freedom. Now, both samples were equal, 40 and 40, so each had 39 degrees of freedom, so it's technically a tie, so we're going to use 39 degrees of freedom. All right, now we just got to build the interval, and this is like the easy part. And as the more and more you go through this, you're like, wow, this is so easy. So first is the difference between my 2 samples. 36.6 minus 28.9 was a 7.7 inch difference. The T star, let me just run through that real quick. Second vars, I'm going to go ahead and hit invert T here. 95% confidence, put 0.025 at the bottom. And 39 degrees of freedom that we discussed. And this is going to go ahead and get us that T star, 2.0227. And then we need our standard error. So the number one issue with standard error is kids forget to square. So please don't forget to square. 12.8 squared was for the northern trees, divided by 40. 15.4 squared divided by 40 for the south. Add those together. And again, type all this in at once on your calculator. No parentheses, just type it all in at once, and you'll get the margin of error. So take the 7.7, which is our difference between our samples, go up and go down by the 6.404, and you do get our final interval. So now it's time to interpret it. All right, once again in red, I can be very generic. I'm 95% confident that the interval between 1.2 inches and 14 inches contains the true difference between the mean diameter of oak trees in the northern states and the southern states, based on the samples taken. But again, that doesn't compare. I don't like that at all. It doesn't do any kind of comparing. I want to give an answer that truly compares. It just makes more sense. So I noticed that the entire interval is positive. Now remember, I did the American sample. I'm going back to the other problem I just finished. Sorry about that. I did the northern sample minus the southern sample, and I got all positive. I got an interval that's entirely positive. What that tells me is that the sample from the north is bigger. So that means that I'm pretty confident that the true difference is going to favor the northern trees. So I'm 95% confident the oak trees from the northern states have a mean diameter anywhere from 1.2 inches to 14 inches bigger than oak trees in southern states, based on the samples taken. So on average, oak trees in the north are bigger. So the researchers have just, I don't want to miss if I want to use the word proven, but they have just justified their thought, or they have justified this idea that, there is a difference. There is a difference between oak trees in the north and south, and it does appear that oak trees from the north are bigger. They could be just slightly bigger, or they could actually be considerably bigger. I don't know what the truth is. It's just somewhere in that interval. Okay. I seriously hope that you find this pretty easy. This is the 4th time that we have explored confidence intervals. We've done them, again, for proportions. We've done them for the difference between 2 proportions. We've done them from a single mean. And now we have ended with finding a confidence interval between 2 population means. So it's going to be important at the end of the day that you understand how all of these are very, very different. Yet they all are going for the same thing. They're all trying to find a true population value. All right, guys, that's it. Hopefully it made a lot of sense. And there is the next topic, 7.7, just dives a little bit deeper into a couple of the finer details here. But again, it covers the same information for the most part. All right, enjoy.